welcome to This Explainer. We're diving into the epic, high-stakes origin story of an absolute titan in modern engineering. Seriously, if you were to picture this like a cinematic anime or manga, carbon fiber is hands down the ultimate protagonist. Okay, let's just get right to the big question here. How does a humble, totally everyday polymer actually transform into an invincible armor that literally conquers the skies? I mean, we're talking about a material that is roughly 5 times stronger than steel, but only a third of the weight. It's the absolute secret sauce behind modern spacecraft, supercars, you name it. Section 1. Origin of a supermaterial. So you might be thinking, carbon fiber was cooked up in some pristine, modern high-tech lab, right? Actually, no. It started way back in 1860. Sir Joseph Wilson Swan invented early carbon fibers to use as filaments in light bulbs. Thomas Edison built on this later, but after tungsten took over, carbon fiber just sat dormant for almost a century. It wasn't until the 1950s that companies like Union Carbide brought it back to life for military tech. That was the flash-forward moment setting the stage for the aerospace backbone we know today. At its core, this stuff is just pure carbon. The atoms are arranged into these massive sheets of hexagonal aromatic rings. If you zoomed all the way in with a microscope, it literally looks like microscopic chicken wire. And that chicken wire packs together incredibly tight, locking into a rigid grid that gives the fiber just ridiculous stiffness and structural integrity. Section 2. The brutal training arc. Like any good anime protagonist, these raw fibers are not born strong. They have to survive a brutal gauntlet. Over 90% of modern carbon fiber starts as a raw precursor called polyacrylonitrile, or PAN for short. This PAN polymer gets dissolved, spun through tiny holes, violently stretched out, and then thermally stabilized in air at around 200 to 300 degrees Celsius. That changes its molecular structure so it literally won't melt in the next phase. And this next phase is intense. Carbonization. The stabilized fiber is shoved into a specialized furnace and heated to extreme extremes. But here's the wild part. They have to do this in a total vacuum, zero oxygen, usually with inert nitrogen gas. Because if there was even a drop of oxygen in there, the fiber would just instantly incinerate. Instead, this heat violently rips away all the non-carbon atoms, leaving only pure, concentrated power. To hit ultra-high modulus strength, which basically means extreme stiffness and resistance to bending, they graphitize the material at a staggering 3,000 degrees Celsius. At that insane temperature, the carbon atoms finally snap into those flawless, crystalline sheets we talked about earlier. But just surviving the fire isn't enough. Next up is anodic oxidation, which roughens up the surface with chemical hooks so it can grip binding resins tightly. Then it gets a sizing, basically a protective epoxy or nylon shield to keep it safe from damage during weaving. After that, it gets wound onto bobbins, completely combat ready. Section 3. Weaving the ultimate armor. So how does this become a physical product? Well, thousands of these microscopic filaments, each one drastically thinner than a human hair, are bundled into units called tows. So if you ever see carbon fiber rated as 3K, that just means 3,000 of these invincible little filaments are packed into a single tow. Then you weave it on a loom. A plane weave is an over-under checkerboard. It's super stable, but because the fibers are tightly interlaced, it has harsh crimps that make the fabric stiff. On the flip side, you've got the twill weave. That's a 2x2 diagonal pattern. Fewer crimps mean it's incredibly flexible, making it perfect for hugging the crazy complex curves of a drone or a sports car without snapping. But honestly, for the skies, standard weaves won't cut it. Aerospace-grade composites need extreme high-purity PAN and have to handle over 700 kilopounds per square inch of tensile strength. They cure these parts inside massive, high-pressure, high-temperature autoclaves to crush any microscopic air voids that could cause a mid-flight disaster. Meanwhile, standard composites, they might just cure at room temperature and a wet layup. Section 4. The high price of power. Now, unlocking this crazy performance does hide a pretty painful reality. To forge just 1 single ton of carbon fiber, you literally have to sacrifice roughly 2.5 tons of expensive PAN precursor. Over half of your raw material just gets vaporized and expelled in the fires of carbonization. Plus, the energy drain is just mind-blowing. Making 1 ton demands a staggering 30,000 kilowatt-hours of electricity. To put that into perspective for you, that is the entire monthly energy usage of 300 average households, just for 1 ton of material.
So yeah, the high price tag is a perfect storm of expenses. You've got raw precursors costing up to $100 a pound, insane energy demands, and crazy specialized tech like 3,000-degree furnaces. Because of this incredibly demanding process, the global supply is bottlenecked to a mere 200,000 tons a year. Compare that to the 1.8 billion tons of steel we make annually, and you start to see why this is such a premium exclusive material.
Section 5. Rebirth. A sustainable future. Every hero needs a redemption arc, right? For years, carbon fiber was a one-way street. It doesn't rust, it doesn't degrade, so it just sat in landfills. And right now, the world is facing a massive crisis of unyielding, indestructible scrap from first-generation wind turbines and old aerospace carts reaching their end of life. But here is the rebirth, the circular economy solution. Scientists are cracking the code with techniques like pyrolysis, using heat without oxygen, and solvolysis, using chemical solvents. They can actually break down those hardened epoxy resins and rescue the virgin carbon fiber trapped inside. Then they spin it right back into manufacturing for a fraction of the original cost. And this isn't some niche lab experiment. The recycled carbon fiber market is exploding, literally projected to blast past $716 million by the year 2035. There's a brilliant quote from the data reports that hits the nail on the head. We're seeing a massive paradigm shift. Industries are no longer just trying to manage waste. They are harnessing true material circularity. We're taking the scrap from an old airplane wing and turning it into the chassis of a brand new electric vehicle. This whole shift is being supercharged by strict new environmental rules, especially in the EU, and the massive demand for lightweight EV armor to boost battery range. Plus, aerospace giants are finally committing to lowering their carbon footprints. Recycled carbon fiber is quickly becoming the go-to sustainable solution. Which leaves us with one pretty staggering thought to wrap up on. We've seen this material forged in fire, woven into armor, and now miraculously resurrected from the scrap heap. As this rebirth technology evolves and costs plummet, will this invincible supermaterial soon step out of billion-dollar aerospace labs and become the unbreakable backbone of everything you own? Thanks for joining me on this explainer. Keep wondering, keep learning, and I'll catch you next time. If you found this explainer helpful in grasping the complex and fascinating engineering, like, share, and subscribe to @Makers Junction on YouTube for more highly professional, basic to advanced engineering content. Keep exploring, keep building, and we'll see you in the next explainer.